Hello, everyone. Welcome to our talk, Multilayer Network Analysis for Improved Credit Risk Prediction. I am Christian Bravo, presenting from Western University here in Canada, and I am joined by Dr. María Óskarsdóttir, recording from Reykjavik University in Iceland. The work that we're going to present today focuses or is motivated by the problem of correlated default. So correlated default is a well-known phenomenon. Back in 1997, the Fed in the US said that evaluating default correlations and the probabilities of multiple defaults, so more than one default occurring in a joint fashion, is an important task in credit analysis and risk management, but it has never been an easy one because default correlations cannot be measured directly. We are here to challenge a little bit this conception. Several studies have measured it indirectly. For example, the citations that you can see in the screen. And it is even used to define the Basel banking regulations. So the banking regulations that rule the universe in this regard consider a correlation between the assets and the overall economy, the raw factors that are quite controversial because they were measured once at one point in the 90s, and no one really knows whether they should be updated or not, right? What we want to do is we want to do this direct correlation measure using some modern data science and network theory. Okay, so it can be measured directly. We already have a paper, again, with Dr. Óskarsdóttir in 2019, where we wanted to see whether risk, right, measured from grade scorings, were actually influenced by effects of other defaults occurring in the network. Right? This was a single layer model because that was determined from call detail records. So people called, that way we knew they were related somehow, and then we also measured credit risk there. There was a significant increase in prediction capability, and we were able to determine a score that said what was your exposure to this network. So back in 2019, we showed that under certain circumstances, we could already measure this default risk directly, okay? But we run into a few problems moving this forward. So we use a network of phone calls. This presents several ethical challenges in order to think about implementing this stuff. We did this from the point of view of researching whether there was any correlation, not really thinking that there was going to be a product coming out of this. But if you want to implement something like that, the ethical questions are really, really strong. We actually have several discussions of that in the paper itself. But are there other networks that can be inferred from functioning that are actually very relevant in this? Well, there are. Indeed, depends a lot on the problem that you are doing. And there is a technique to use that's called bipartite models. You can see the papers by Van Flassler et al. In 2014 and 2015, Management Science and Decision Support Systems, that discuss this technique to separate the networks between different elements and the individuals that you want to measure. The problem with doing this trick is that if in a normal circumstance, you will end up with a lot of clicks. So everyone will be connected to a particular place, for example, right? That's not really helpful from a network point of view. So we got to the solution that we're presenting for this paper, that's multi-layer bipartite networks. I am going to motivate this in the context of agricultural lending, but this is not only applicable in this world, right? We are actually right now conducting experiments of this in many, many other places, and I am happy to discuss this afterwards in the discussion session. So our problem is the following. We are giving loans to farmers, right? And they are subject to structural risks that can correlate depending on where they are or what they are selling. So, for example, the black goo plague affected a large number of vineyards in California in 1999. That's product correlation, right? A drought in California cost around 1.8 billion per year and 10,000 jobs, according to a UC Davis study. And that's a place correlation. There was a drought in a particular place and everyone was affected by that. And finally, those two things can actually intertwine and expose you to a higher risk. For example, there was a set of floods and drought, right, in India that caused a large issues in rice plantations, right, according to the Economic Times. This can be, here you can see the place and product correlation and how these farmers actually relate themselves. We had a decently sized data set of 70,000 agricultural loans with information from the loan, from the previous history with the institutions, other past loans, other past repayment history, we call this the behavioral data set, and some product and geographical area information that we use to construct the networks, which is going to be explained right now by my colleague.
Thank you, Christian. So I'm going to tell you how we actually constructed our network using the data. So first of all, we connected each farmer to the district in which they were located. So in this figure, for example, you can see 7 farmers that are connected to 2 districts, A and B. And then similarly, we took the products which these farmers were growing, and we connected each farmer to their product. And this creates a product layer of our network. And here you can see how we then connected the 2 layers together by linking each farmer to themselves in the 2 layers. So here we have a multi-layer network where the first layer is the district layer and the second layer is the product layer. Now, in our previous work, we have been using personalized PageRank measures in order to rank nodes in terms of importance in the network. And we can do this in order to bring out nodes that are important from a particular perspective. And in this particular case, we are looking at being important from the perspective of default. So what we're actually doing is spreading default influence through the network and obtaining scores for each and every node in the network. And for this, we use, as I mentioned, the personalized PageRank algorithm. And here you can see the equation for that. So in this equation, key is the personalized PageRank scores, which each node obtains. And it's calculated based on 2 factors. So the first factor is the spread of influence in the network itself. So how information travels in the network. And then we have the second part, which is the actual influence spreading itself. So here we can code the influence from prior defaulters into the algorithm. And what we get as a result of this is a score for each node in the network that indicates how exposed to default they are. And this algorithm has been applied, for example, in fraud detection in order to find nodes that are a high risk of being fraudulent. And also in our prior work, we have done it to detect default in networks. So we actually had to invent this algorithm for multi-layer networks because it did not yet exist. And here you can see how we did that. So the nodes that have the X on them, these are the prior defaulters in our network, and they are the source of influence in the algorithm, the ones that spread the default information in the network. And as I mentioned, this algorithm did not exist for multi-layer networks. So that's one of our main contributions was how we adapted the algorithm to multi-layer networks. So the equation that you saw before gets changed to the equation that you can see here. So it's a bit more complicated. And if you want to learn more about the details of that, I encourage you to read our paper. But we used this algorithm to spread the default influence in the network. And we obtained an exposure score for each node. So not only the borrowers, but also the products and the districts, which we represent here with different notations. And this is for each and every time step in the data. So we built networks that each spanned 5 years, and then we had like a moving window of these 5 year networks. And once we had calculated these PageRank scores for every node in the network, we could use them in our network featurization process. And that's when we extract information from the network to put into a tabular data set together with the loan information that we had. And here you can see an example of the variables that we extracted. So we used, for example, the PageRank score itself of the node. We looked at the PageRank score of the product to which this farmer was connected and to the district to which it was connected. We looked at the neighborhood to see how many of the connected nodes had defaulted before, and so on. So we extracted a whole range of different network variables from our network. And then once we had extracted all of this to enhance our data set, we started our credit risk model building. And we considered different groups of features. So we had actually two applications. So we had first the baseline features together with network features. And then we had the baseline variables together with behavior variables and the network features. And we tried different combination of these using two different supervised learning models, which were logistic regression and XGBoost. And we measured their performance using AUC, and to interpret the results, we used the Shapley values. And now back over to Christian.
Thank you, Maria. So now let's go see the results of the models that she just introduced. The first thing that we can say is that multi-layer networks actually help a lot prediction. We see an increase in the best case of around 12% in an XGBoosting, right, over a baseline model with no network variables. However, here is another interesting result. Even using naive results, so that is, even using just the variables from the single networks without a multi-layer propagation, already gives you a very good increase, 9% in one case, of the lower part of 11% on the other. However, if you really want to get the extra prediction, you need to add this personalized PageRank measure that we created. The other interesting thing that happens here that's not surprising is that behavior variables are very strong, even in the presence of network variables, but still the network variables allow you to gain 2 to 3% extra predictive capability. Right? Now, if you enter the variables, the variable importance, you can use the Shapley values. Here you can see how important the variables are to predict default, right? So the center line, the 0, measures no predictive ability. To the right means that you are predicting more defaults. To the left, that you are predicted more non-defaults. And what you can see is that connectiveness to defaulters. So the first two most important variables are how connected you are to defaulters. That is the evidence of correlated defaults. The networks are created with past data, and they are used to predict future data, and past defaults within your network are the strongest signals. And this was a very surprising and very interesting result. And there is one variable for each of the network. And actually, this is another interesting insight. The area network is more important than the product network. So where you are is more important to correlate the defaults than what you are selling. Makes sense, right? If there is a natural disaster, in this particular case, it will impact a lot more. That's also relevant from the modeler points of view. What networks you use are going to be extremely important in identifying what are going to be the effects or the gains that you're going to get for using network variables. And finally, if you count, the fifth most important variable is the personalized PageRank one. So we can see that this is highly predictive, right? And the traditional variables only appear right further down the list and then below. So yes, network variables are important. Default does correlate. Finally, just to show you the impact of a couple of these variables, going a little bit more into detail. So highly connected individuals that are very highly connected in the network, right, which are the ones that have a high, that are right here, they present better behavior than the average borrowers. But individuals highly connected to previous defaulters that we can see right here are at a higher risk, right? And we can see this non-linearity. This is also something that got our attention. These are not at all linear behaviors. And finally, looking at the page ranks, the multi-layer scores seem to be excellent prediction of good repayments at low values. So if you are not exposed to defaulters, which are the ones that you can see right here, you will most likely not be a defaulter yourself. And that's a signal that we're capturing, right? So that's something really interesting to get out of this. And that's that. Our takeaways. Multi-layer networks are much better than single-layer networks. It makes sense to use the networks if you have them, all of them. Even naive multi-layer analysis, even if you don't have the capacity, the computational capacity or the time to calculate too much, just using centrality measures are very relevant for this, right? And the bipartite trick to create networks, even when you seem to only have clicks, so connections that seem to be very concentrated, by using these bipartite tricks and using multi-layer networks, you can create these network complex structures, right? And it's the exposure at defaults that impacts heavily credit risk. As we wrote in the paper, friends seem to be more important than money or your own intrinsic risk in this case. You can find the paper in archive. The paper is almost published already, so it's going to appear at a journal soon. I don't want to spoil it, so I'm not going to say what journal it is, but possibly by the time that you are watching this presentation, the paper is hopefully already out there. Still, you can always find it in the link right there. Thank you so much for your time, and I'll be happy to answer any questions you have in the discussion session afterwards.